All right. Good morning, afternoon, evening, wherever you are in the world. Thank you very much for tuning into what we're calling the Generative Methods Day. So I am Professor Jim Whitehead. I am a professor of computational media here at the University of California, Santa Cruz in Santa Cruz, California. For those of you who have no idea where Santa Cruz, California is, it is located on the Pacific Ocean, about an hour south of San Jose, or about an hour and a half south of San Francisco. We're on the Pacific coast of so today we have 9 talks for you about the generative methods work that we're doing here at UC Santa Cruz. And we decided to do that here today, 2 days after the end of ProcJam, to celebrate ProcJam and to kind of let people know about the interesting work that's going on here. So we have talks that range from kind of very concrete techniques like Wavefunction collapse, going to be presented here in a minute, to more leading edge research ideas that are kind of more speculative and haven't entirely been cashed out yet. So, so you'll get see a real spectrum of work here today, all of it being presented by PhD students here in computational media. And I suppose this is as good a time as any to put a plug in and say, you know, hey, if you really like procedural content generation and think it would be really fun to do this for a living, getting a PhD in computational media is one way to get trained up and to get the kind of credentials you need to be able to do this for your profession. So we are accepting applications now for our master's and PhD program here in computational media. And there's we'll be showing the link every now and then. Okay, without any further ado, let me introduce Isaac Karth, who's going to give you a brief introduction to Wavefunction collapse. And again, thank you very much for watching. Which one's live? You're over.
Okay. Hi, I'm Isaac Karth, and I'm here to introduce you to Wavefunction collapse. If you were active on Technical Artist Twitter around the end of 2016, you might have seen some animations like these. These were generated with a technique called Wavefunction collapse, an algorithm invented by Maxime Gouman, a roguelike game developer. It's a data-driven image synthesis algorithm that produces results with surprisingly consistent styles from a single example image. As you can see here, the small handcrafted source image on the left is being translated into this larger assembly that recontextualizes the smaller parts into a new, larger image that still has that same style source. Texture synthesis isn't a new idea. The general problem has been studied in universities for more than a decade. But unlike most texture synthesis, which uses blending between pixels to approximate the image you're going for, Wavefunction collapse uses exact matching. It extracts more style from less data by paying close attention to the input, and borrows a lot of ideas from street model synthesis. But rather than the 3D models, it operates on a wide range of data and different graph. For example, people have used it to implement level generation directly from Unity game objects, or to do poetry generation that respects rhyme and meter. It's also been generalized to 3 dimensions, such as this example on the right from Oscar Stahlberg's Viking invasion game, currently in development, called Bad North. And it's been combined with other forms of procedural generation, such as Caves of Scud use of Wavefunction collapse as part of a multi-phase dungeon generator that not only uses it for the visual output, but respects the semantic gameplay information as part of the generation. The basic loop of wave function collapse makes choices and then spreads the implication of those choices. Here I'll show you a quick demo using a mock-up that Oscar Stahlberg has put together. Here we can see on the left the blocks that we're going to use to build our new world, and on the right an 8x8 grid of potential tiles showing all the possibilities that could go there. Here I'm going to choose to make this one dirt, and you can see that it immediately spreads the implications of that choice the rest of the grid. If I say I'm going to make this one here sky, it does the same thing, automatically figuring out that this is the only remaining valid choice. So there we go. Helps if you have the mouse on the right screen and not looking at the recording of the mouse. So this is the basic core loop of wave function collapse. When it's actually in practice, it uses a heuristic to make the choices instead of you're manually making the selections. So the entire process is automated. If we revisit those animations from the start, we can see that they use the same choice and propagation loop. And that's all you need to create these complex images that have the style of these simple little input images. While this choice and propagation loop may seem unfamiliar, it's actually a common thing in constraint solving. Some examples are on the right, Nagra, which is an intelligent level editing tool that uses an existing constraint solver to extend a level design sketch a guaranteed playable level. Likewise, the generator for refraction here on the left generates puzzles that are guaranteed to be solvable. Both use technology that works very similar to wave function collapse. And in fact, we were able to re-implement wave function collapse in ASP, which is a programming language dedicated to expressing constraint solving problems. Here in this code, we say what choices are allowed to be made and what constraints apply to those choices. Viewing wave function collapse as a constraint solving algorithm also allowed us to easily drop in additional constraints without changing the algorithm. For example, if we're using wave function collapse to generate a level, we can guarantee that there's a traversable path from the entrance to the exit. Controlling the traversability of wave function collapse results is something that people on Twitter and developers who are looking to use this are very interested in. Adding additional constraints gives you more control for what kind of generation you get out of it. It's a very popular question for people to ask if anyone solved yet. Adam Smith and I aren't the only ones exploring wave function collapse. Developers have used things like finding looping animations and have experimented with a number of enhancements. This includes people here at UC Santa Cruz, for example, Joe Mazica, who you'll be hearing a lot more from today, who's implemented reachability constraints in her tile-based map generator. In conclusion, I look forward to studying how algorithms such as wavefunction collapse are being used by developers, and also explaining why they work and how they can be used. Thank you. Yes.
So like wavefunction collapse works best when it has files already working.
So the question, the question is, does it work better when you already have a set of constraints,
Yeah.
or
Menu option.
yeah, it's the whole idea is that it's based around having a constrained set of inputs. Now it can take, for example, an arbitrary set of inputs and analyze that to figure out what the constraints are. So a big part of this is that developers are really excited that they don't have to lay out these constraints by hand unless they want to. It has been used. You can actually do things like chain wavefunction collapse together with wavefunction collapse or another algorithm to create the data that you're going to input. And actually, Caves of Cud uses a little bit of that in their
How much impact does starting?
You mean not the starting source image, but where the algorithm chooses to start? Because you can choose, I'll put the caveat that you can choose to write the propagation and observation steps in a number of different ways. But since it's basically a Markov process from which tile you choose to start from has a huge effect on exactly what output you get. It can be run entirely deterministically, with a fixed seed, but it does affect what results you're going to get from that run of.
Up next, we have Bardo augmenting D&D adventures with.
All right. Hello, everyone. My name is Lucas Ferreira. I'm a third-year PhD student here at UC Santa Cruz. And okay. So yeah, today I'm gonna talk about Bardo, the system we are creating here to augment D&D adventures or tabletop games with generative music. So for those who are not familiar with this kind of game, so tabletop RPG games are narrative-based games where you have Dungeon Master, which is guiding other players through an adventure, and then all these players are creating this adventure together by speaking and taking actions. So the DM has this role of explaining the situation or telling the initial state of the story, and then the players have to take actions, and then the narrative develops like this. And to motivate this work, or why generating music for this kind of adventures, I want to show you 2 brief videos. And this is like one DM telling one scene of the story.
As cult leader drives the dagger of man's heart, there's a white flag.
I want to show you another video. Oops. Yeah, that's what I'm trying to do. Can you help? Over.
We're not recording desktop audio right now, so
sorry about that.
no worries.
So this. Oh no.
That's it.
Yeah. I want to show the same story. Now, music.
Cult leader drives the dagger into the man's heart. There's a white flash.
So, well, as you probably could feel, the having adventure like that with music is much more intense for the players, and it adds more to the experience, because music is capable of like giving us emotional information that wouldn't be there only with speech. So coming back with our adventure here, the goal of this work is to generate that music that you hear in the background in real time to augment the player's experience. So our approach here would be to add some sort of insert in the scene or in the game a device that could hear the speech of the players and also react to that, somehow extracting information from the speech and then composing music for them based on information that the system get from them. So our vision here, so the main vision of this work is to augment players' experience with generative music, but also we think that this could give us a bit more in a general sense. If you think you could support music composition through speech, if you think of it in an interactive kind of system, you can think of this system as a musical instrument that allows you to make music through stories. So you could use this in other settings as well. Moreover, we can think of this as a support for automatic music composition for creative writing in general. Once we use speech or text, as input, we could use other types of narrative like novels, poems, and movie scripts and generate music for them. So currently, we have a system that is doing music recommendation for tabletop RPG games. We haven't tackled the problem of generating music yet, but in the current state of this project, what we're doing is we are extracting the speech of the players of videos, actually, of tabletop, of D&D games. They look like this. Let me show it briefly a little bit. Oh. So what we do is we use the Google speech recognition system to extract the captions of the videos. And then you don't have to keep playing this. I can just mute. And we create a data set of captions, which are labeled according to four categorical emotions. I'm going to explain that later. And we use supervised learning here to then classify new sentences that are given by tabletop then players for D&D players in the future, and then we pick handouts or songs that match that given emotional state that the supervised learning algorithm predicted. So let me explain this a little bit more. So the data set that we collected looked like this. So we have a bunch of sentences that are organized here according to the sequence of the narrative. All the labels are possible for 4 different emotions. We have here calm, suspense, agitated, and there's another one which is happy. So what is important here is to see that these structures don't have any structure. So we don't have access to like punctuations. We don't know when is the end of a sentence. We don't have commas, anything like that. We just have the sentences that they come from the speech recognition. And we might even have like grammatical problems here, or even like mistakes in terms of words. This is a big issue that we have to tackle in this problem or in this project. So for those who are not familiar with what supervised learning is, I'm going to just like briefly explain it. So here we have that label data set that is split in two data sets. One is called training data, the other one is called testing data. And the training data is used to train what we call train a supervised learning algorithm, which try to extract correlation between the data and the labels. And then this gives you a predictive model that you test by using the testing data. And this gives you an accuracy. So with this approach, you can measure how accurate the system, your predictive model is. And in our case, so the data set looked like that, the one that we gave, we split that in a certain way. And for the predictive model, for the algorithm here, we use naive Bayes, which unfortunately I don't have time to explain, but you can easily look it up and find how it works. For measuring, for experimenting or finding out the accuracy of a system, we trained naive Bayes with 8 episodes. We used 8 episodes as our training data, and we left just one for validation. And we compared this naive Bayes approach with a lexicon-based approach called emotion density, just for the sake of comparing something to see how this is a very naive, also even simpler algorithm. So we got an accuracy with the emotion density, we got an accuracy of 49%, and with our method, we got an accuracy of 64%. Again, those are considerably good accuracies considering like the lack of structure in the data set. After that, we ran a user study comparing the performance of both of our methods in comparison to the music that were already there in the videos. So what we did was we asked users to evaluate the music selection performed by our system against the music selection that were initially there in the videos. And the possible questions were possible answers were video 1, video 2, equally appropriate. So the results you got, they are pretty successful. The results show that our system performed better in 4 out of 5 episodes. And looking more deeply into this, we can see that in the bottom row, we have the accuracy of the system in actually predicting the labels of a given episode. So when you performed really poorly, like for example, in the episode 2 here, you have 20% of accuracy, but you still were able to create a best music selection for that video. And when we performed really well, we also were able to beat the human music selection. But interestingly here, when you perform in average, we perform worse. And those values here are correlated with how difficult it is to predict the labels of an episode. So for future work of this project, I'm going to tackle how to actually use the predictive model to generate music instead of just selecting songs. So, and after that, you're going to evaluate the system with real D&D players in real time. And I just want to acknowledge my collaborators and my advisor, Jim Whitehead, and the funding from Brazilian CNPq funding agency. And thank you. I'll have to take questions.
Okay.
It's moment by moment. We treat this problem as like kind of a state machine, find a state machine problem. So you can think of it as also some sort of or like online supervised learning, because we actually feed like each sentence by.
So it's not
Yeah.
flipping
No, it's not like no, it's not like oh, if the system decides to change, then it changes like, and then it can change every sentence. No.
How do you plan on generating ideas about like actually start composing on the fly?
Yeah, my initial thoughts are, so the big issue here is, so we are trying to use like video game music scoring techniques for doing that. And the problem here is that you have to extract some sort of like the graph scene or of the story. So we have to figure out, for example, when transitions happen. Right now we are using emotions, and you could assume that whenever there is a big motion transition, you could say, oh, this is a new scene, but that's not that true. So what we're trying to do is somehow, instead of just analyzing emotion, we're trying to discover what is happening in terms of gameplay in a given scene. So basically, for example, in the beginning, you have an introduction of the scene. This could be considered like a gameplay part of D&D. And then you can go to a battle, and then from the battle, you could go to an exploration mode. And the exploration could have like a resolution, and maybe you could have a boss fight or something like that. So we're trying to extract actually the scenes, and then from each scene, we use like emotion information to compose the music, and then we are looking for like techniques such as either grammar-based or search techniques. So we are trying to come up with a way of searching for songs that having a given emotion. So we are trying to move on from the categorical model of emotion to a more dimensional model of emotion, and trying to use some sort of like way of calculating emotion of a given song. So then you can search for songs that have that given. That might be an issue to run in real time. Another approach might be something like creating grammars that compose music for certain emotions, and then when you have a transition in this scene graph, you pick the grammar that represents that emotion, and then you somehow have to figure out how to do like maybe modulations between scenes.
All right. Next up, we have Adam Somerville, who will be presenting about Gemini, a bidirectional game for understanding / generation system, for game understanding / generation system. If you give me 1 second to... well then. Different PowerPoint. My bad. Apologies. Oh, you're. That's. I'll give you the computer and take it away.
Hello, hi, I'm Adam Somerville, PhD here at Santa Cruz, and today I'm going to be talking about Gemini, a bidirectional game understanding and generation. So there's been a bit of work in the field of sort of automatic game generation, and a sort of small subset of that has been focused on generating games with meaning. I think all of us know, or hopefully a lot of us know, that games can carry great meaning in them. And so people have tried to target this, most notably Mike Cook and others, Angelina, and Mike Trainer and others, Game-O-Matic. But the way that these systems work is that they take some sort of set meaning at the beginning, either set out by a user or the system comes up with it on its own, and then tries to generate a game that matches that meaning. But they never actually check their homework. They never actually look to see if the game that they've generated actually does what they say it does. And so they haven't closed the loop. And so sometimes, these systems can make choices that, in combination with other choices that they're not fully introspective of, wind up sort of going against the targeted meaning. So that's what Gemini intends to fix, to actually close this loop and sort of verify that the generated game actually matches the supposed prescribed. Now, how do we know what the meaning of a game is? So the system, Gemini, uses a sort of operationalization of a humanistic practice called proceduralist reading, set forth by Mike Trainer and others. Now, in proceduralist readings, a game is a set of definitions, the stuff in the game, the entities, the resources, and then the mechanics, how they move, what happens if two things collide, does a resource go up or does one of them disappear? And then there's a process of actually sort of extracting the meaning. So from those, you can sort of get the dynamics of the game. So, pressing a button makes Mario go up, and when Mario hits a Goomba from the top, the Goomba disappears. But that leads to the dynamics of Mario will jump to on top of a Goomba. And then there's the aesthetics of, a player will do this because it's a pleasurable act. It has a nice noise to it. And then there's the theme that plays into those aesthetics. There's a nice sound that plays when you squish a Goomba. So it's, enjoyable act to do. And then all of that can lead into the meaning of, destroying Goombas is a wonderful thing in the world. Or maybe it leads into a meaning that the game did not intend. And these meaning derivations can sort of build on top of each other and chain into higher and higher until you can sort of describe the game in one word or something. And of course, all of this is informed by the cultural context that it exists in. So, in one culture, green might seem, or in one context, it might seem that green is life and verdant and growing, and in another, it might be sickly and poisonous. So, all the while, there's culture pushing its sort of fuzzy blob on top of everything. And so, by sort of proceduralizing this process, we can try to derive the meaning from a game. So, the system uses a domain-specific language that we made up called Cygnus, which I'll first discuss so that the rest of it will make sense. And then I'll go into how we do this sort of meaning derivation process, and then finally get to how Gemini generates. So as I said, a game is sort of a set of definitions, the entities and the resources found in it, and then the mechanics, which we define as like a set of preconditions, and then if all of those preconditions are met, the result of that. So in this case, if the player holds the up arrow, that leads to the outcome of moving up. Moving up doesn't actually mean anything. That's just a unique signifier here. And then that results in the entity called paddle left, which again has no actual semantic meaning. It's just a unique signifier moving one north. But so things like up arrow and held and north are semantically meaningful. The rest are just unique signifiers. And so now, sort of getting that overview of the language, I'll go about the procedural reading process. So all of this uses answer set programming, which you've heard about before, and we'll hear about again later on today, I'm sure. We like that stuff. So we have rules. So like maybe we want to figure out like a pretty low-level inference, like what does the player control? And so we have, the player controls X if there's a precondition that there's a control event that leads to an outcome O, and then the result of O is that X moves in some way. And so this is just one way that we might say that the player controls something. There's lots of other ways, and those would be codified by different rules. But inside of games, this rule might be reified by, the player controls the left paddle because when they hold up, it moves north, or the player controls a bucket in Kaboom because when they hold the left arrow, the bucket moves west. Or, in some sort of asteroids-like thing that when the player holds a button down, it moves forward. So these are all different ways that this would be found inside of a game. And so that's a pretty low-level one, but, we can, as I said, we can chain these up. And so this is actually still a pretty low-level reading, but it's about what will the player do up at the top, and then, sort of going up from the bottom, we take the base facts, mechanics of the game, and then chaining those together with rules, we can, build up these higher-level inferences. I won't get into this in depth, but we can go many, many orders higher of this, but this is just sort of a simple example. So that's how we actually look at a game and try to figure out what is actually going on, but now how do we actually generate? So inside of ASP, there's essentially these curly braces mean like there's a choice. And so we throw up our hands and say to the computer, okay, you get to pick something here, and subject to, we say what types of thing it can be, and then other constraints. And so Gemini is really about making choices of what are the preconditions, and then what are the results. And then, those conditions could be things like control events, or two things overlapping, or resource thresholds, or in the actions, the results of those can be the entity moving, or looking in different directions, or rotating, or being added or deleted, or resources changing. And so there's sort of this giant primordial ooze that Gemini the ASP gets to sort of pick from randomly, subject to other constraints. And so we have a large set of constraints that sort of are basic common sense level constraints that, if we just sort of randomly picked a bunch of stuff for rules of a game, there would be a lot of nonsensical results. And so things might be like, you don't want to have an action that decreases a resource by itself, because that's just setting the resource to 0 in a really roundabout way of doing that. We don't want, an outcome to be unreachable. Of course, unreachable is a whole other set of rules about, what are ways that an outcome might be unreachable. Like, for instance, say the only precondition to it is that two things overlap and neither of those things can move. Like, that can never result in a reachable outcome, and that's just sort of a superfluous rule, so we don't want to generate those. And, it might be that we need preconditions. We don't want to have there to be 0 preconditions for a given outcome. And, there's lots of these and lots and lots. We have like over 250 common sense rules that just try to sort of carve out the space of generated games to something that actually is interpretable by humans. But then that's just to sort of generate like playable games. We actually, want to be able to target certain things. So then we have what we call design intents, which are a set of constraints set forth by a user that specify like what they want in a specific game. In this game, it's, the game must involve hand-eye coordination. There must be a control event that has risk and reward. Resource 1 must be seen as good, and the game must involve maintaining a high level of that. So these are all the sort of different types of things that we can find inside the game. There's lots of other things that we can have. One example, design it. And so that leads to a game here, which unfortunately I don't have a lovely good GIF of. But the game involves controlling the red circle to overlap with the blue circles, all the while the green circles are chasing the red circles. So the goal is to, sort of weave in between the green circles while overlapping with the blue, which results in the resource 1, which in this case is labeled composure, staying high. And so now to sort of discuss some lessons that we've learned in the years of making Gemini. And one of them is that generating is somewhat easy. Like, if you want to just hit a button and generate a game, that's easy, but actually trying to understand what's going on in that game, particularly with using ASP, so we're trying to sort of like statically analyze a game and understand what's going on. And that's really hard. So that was the sort of first year and a half of this was all just doing the understanding process. And then from there, hitting the generate button has been a lot easier. But in part of that is that codifying common sense is also very hard. Like, we don't think about all the things that have to happen in a game for it to be, interpretable to humans. And so the way to figure this out is that we actually have to play the game. And so that leads to the last one of that the phenotype is not the genotype. Like, we can look at the rules, and sometimes like you might look at some rules and they seem perfectly valid and perfectly great, except like maybe it's that one thing is chasing another, and you're like, oh, well, so this game will be sort of tense, and one thing's chasing another. Except if the things that are being chased like always run into the corners, it's not really a game of chasing anymore, because now they just sit there and there's no action or no intrigue. So you actually have to play the game and say like, oh, well, we don't want them to run in corners. That's the thing that we don't want, and that sort of helps build up this common sense database. So yeah, that'll take any questions.
Sure. So, yeah, in direct result of Gemini, it's a set of rules. Here are the previous. Turn that into playable.
Yes, yes. We have a. There's other things too. The core of it is generating these rules. There's also picking what entities there are, picking sound effects, picking what they look like, etc. But yeah, the core of it is the rules. But yeah, we have a compiler that takes in these sets of rules and then spits out playable JavaScript code using the phaser library.
So how much you find someone game assignment traffic? That's actually not so.
So I think it's both, right? I think that it's so like there are like that's like what I said. Like we have like sound effects and visuals and stuff, which are part of it. And so I think it's really like you could have like the just purely like aesthetic like signifiers that I think and you could be convert like the mechanics might speak against those, which would lead to a different type of like a different meaning than like if it's it seems really happy except it leads to you losing the game. Like I wouldn't say like it's like, oh well, losing the game is a happy thing, like, or maybe it is, but it like I think it's really requires both of those in synthesis to sort of derive what actually the game is to get across. Okay, thank you.
All right, it's me again. Next up, we have Chandranil, who will be presenting on a bunch of question marks, computational generation of surprise. And if you give me 1 second. Great. I'm going to pass the computer off to you and take it away.
Thank you, Jonathan. Show. I'm Chandra Neal. I'm a PhD student at UC Santa Cruz, advised by Jim Whitehead, and I'm going to talk about what the computational generation surprise games. So, human beings are hardwired to enjoy surprises. Surprise plays an important role in demand for new content, in media, and other sectors. Helps in player engagement. And a lot of games already use this emotion to create an engaging experience. But however, generated games have often found to have some degree of sameness to it. So after a while, people get bored out of it. For example, there's a recent game called Man's Sky, which although had a lot of hype, failed to live up to it. Because a huge part of it was failed to keep the players engaged. So before we talk about surprise, the basic part is expectations. So based on how players see the game, they form some expectations out of the game. So here we see a Goomba moving horizontally from left to right. From this, player expects that this is how Goombas would behave in the game. When they see flying Goombas or moving horizontally, it kind of violates their expectation. This violation of expectation based on cognitive modeling, cognitive theories of cognitive science, of surprise will surprise the players because it violates or breaks their expectations. They can also be surprised when they're caught off guard. So here we see a game called Splunky, which has sticky traps, which is marked on the red box. So whenever it gets triggered, it's a kind of sticky trap. It shoots an arrow and it kills the player if it hits the player. So here, the player, while while playing the game, might overlook it, and whenever this trap gets triggered, they get surprised. So this is an example of surprise because they were caught off guard. Here's also another example. So when he's too much aware of the ticket trap, he might not know that, might not realize, or might totally forget there's a trap downstairs and killed. So that is also when they're caught off guard because the entire information they kind of was overlooked by them, because it inherently happens because we cannot take in all the information that is available to us. We have some sensory perceptual limit of information that. So based on these two, I came up with a definition of surprise. So a player gets violated when either of these two conditions gets either because of either of these two conditions. When one is when their expectations are suddenly violated, or when the player is caught off. And in both of these conditions, a player learns from it, and the event causes. So we performed a user study in a game called Splunky. It's a roguelike adventure game where a player has to basically find an exit path from an entrance, and they encounter a bunch of enemies. And we created a user study. We began recruiting 22 subjects, 17 male, 5 female, and they were all grad students ranging between ages 20 and 39. Each subject played a few tutorial levels, and we were asking questions about why they were surprised. So this was the goal of this user study was to find out information about what is surprise, basically do a survey of what is surprise, how do people surprise. So we recruited these user subjects, they played through the game, and we recorded the video recordings of their facial expressions and also their gameplay. And later on, they went through the video again, labeled the surprising moments for us, and also said why they were in the textual. They also answered an online form, which took the demo. So we found that approximately 21.3% of the subjects were surprised because they were caught off guard. The rest were patients, and these were all the reactions to surprising. So you see, 40% of them approximately had no reaction. There were no visual reaction to the surprising events, but they labeled that they were surprised. 15% were non-verbal. 7% was non-verbal, and around 40% was verbal. And 15% of them, they had both verbal and non-verbal. And let's piece out the non-verbal reactions to surprise. Most frequently surprising reaction was head tilted backwards. People also raised their eyebrows. People also dropped jaws, and eyes were open. So these are some of the classical responses to surprise but only in approximately 20% of the cases of the surprising events we found, we had a non-verbal. The rest were either verbal or no reaction. In the terms of verbals, people use screams, gasps, use expletives, and sometimes crocodile laughter, which is actually the most commonly expression, right? And we also found out the frequency, found a nice cluster of two types of people. Like some people were highly surprised, some people were less surprised. So the mean of these surprising events were approximately 10 surprising events, but we see that there is hardly anyone in that sector. Most people were either more highly surprised or less highly surprised. So there was a huge standard deviation. Standard deviation in terms of frequency of surprising events was close to 5. So using this, we can find that the experience of surprise is highly diverse. Some people, it depends on the personality of the people, how they play the game, and this is how two clusters we found. So based on this, you can find a model of surprise. We call it VCL model. So as a player plays the game, they continuously use their prior beliefs, like which stems from how they play the game, how they played games in the past, and if people get surprised when they are caught off guard or their expectations are violated, and this happens when there is a significant update to the belief, or if the new event is antithetical to their existing belief, and this causes learning, which causes update. So using this, we are working on towards an implementation of this model. So we currently have some assumptions that player has no prior expectations. So we're expecting that all the expectations are built as a game, and belief updates are surprising, and all the actions that the player takes while playing the game is a response to the player. So the model works out the implementation is like this. The player plays the game, we analyze the data, we generate the belief stack. We'll talk about it, what is a belief stack, and then we make changes to the level, we perform some mutations and present and check whether it's still playable or not, and present it to players and surprise them. So how does this work? So let's first talk about what is a belief stack. So belief stack is a quadruple of stacked elements which has 4 parameters: agents which is defined as the game element which the player is interacting with. It can be a Goomba, it can be a pipe. These actions, these finite set of actions, a Mario can, for example, a person can take. In case of Mario, walk right, left, jump, duck, and sometimes there's a secondary action, which is basically when you hit a turtle, it kills another enemy, so that is a secondary action. These are the actions it can take. There's interactions, player can take damage, can kill or damage the player, so on, and the result can be success or a failure. So if player chooses to stomp on a Goomba, the prior belief which is generated is mushroom, walk right or jump, and it damages the player. So if it walks on a Goomba and gets died, it would be Goomba, jump, damage, and a success. So let's see how it works. So here, this is what I was discussing: Goomba, jump, and kill, and a success. So what we are doing is we're inverting these parameters so that player gets surprised. So in this case, if a player jumps on a Goomba and dies, so in that case it would be Goomba, jump, and it would take damage, and it would be a failure. So we are trying to change the interaction parameters to make sure that the result parameters change. So using this, we are creating surprising. So the work in progress is right now to validate whether the belief stack we are generating, if the players are in agreement with it, and using this to generate new surprising levels presented to users. We are also trying to cluster different types of surprise and what is the reason why there is a huge difference in the clustering of why some players are more surprised, why some players are less surprised, and find out the divergence. Divergent factor is basically why there is this difference. So we are trying to find out what are the features which are of surprise, which makes it more surprising, and less surprising. And that's it. I'll take any questions.
Again, you talked a lot about like, building understanding, but how do you plan on generating stuff?
So what we do is we divide an element as a matrix of game elements. So each element has a set of parameters, and those parameters we are trying to change. Like for example, a change in the parameter of a Goomba to make sure that its behaviors change, so that whenever a player interacts with it, have a different. So that's each element. So for example, a pipe which is static can be made dynamic by changing the interaction parameter or how it works. That's right.
So game prize model prize.
Yes, I think so, but we have to, in that case, so this model is built for platform games, so all the parameters like for the belief stack is generated specific to platform games. The belief stack in that case would be changed to fit that. So it requires in short, it requires a lot of domain adapter.
Follow-up. Are there
Every game, I think every game has a potential to be surprising if you make enough changes to it, because every game builds a set of expectations and you have to validate. So any unsurprising game, such as even board game, can be made surprising by violating the prior expectations about, like, for example, if you can make a game like, and player suddenly realizes there is no winning condition, then player would, oh, what happened? Might not be. Surprise can also be positive, negative, and neutral, but can that's the questions.
All right. Is time for our presentation before we take a quick break. Well, I mean, it is part of the rhythm now. But we have Melanie Dickinson.
Very much, and thanks for the organizer. This has been like remarkably fun, and like you have like everything going so smoothly. I'm very impressed. All right, so my name is Melanie Dickinson. I third year, and this is a kind of side project, ongoing side project. So it's less technical talk and more of a provocation for rock jammers out there, and maybe give you a glimpse of threads. So yeah, again, the design provocation, sort of general strategy, generating a task, specifically focusing. So a lot of existing generative systems that are somehow about social are often focused on individual, generating very rich models for individual writing going on. This is on the lower end character, but it's squishy. So this is it's about me on for a metropolis of their civilization, and it's not at all the focus, but there's just sort of list of individual kings that you have. One of the have like Hills, Oreo Scratch, that sort of stuff. sometimes sad face specific skills and all that. But it's just begging for interaction. Sense of like, why are there? I think that if there was sort of a little blurb what's happening in the world about how they're interacting. Another example is also this is a generative system which is more explicitly focused on interaction between virtual characters, but which also kind of emphasizes digital. So you can compare a description of one. They have sort of a personality model, a look like, but you kind of have to interact as a interactive system. How they will interact with it. That's kind of the magic of the bad news. Mixed physical. So Sims, another one, but now instead of so now we do have some model of relationships between, but of course they're bad sliders. When sliders for go thresholds, you friends, which is I love Sims and all of socially focused playable experience. That's why there are definitely more narratively rich relationships to model. You need a thing for me?
The audio.
Yeah. Oh, right.
Yeah. Ring.
Ooh.
Yeah.
Not my voice.
Yeah, so
Okay.
I don't think it's actually. Are we getting audio again? Okay, we're getting audio again. Hopefully this works. Please let us know in the live stream chat if the audio continues to heck up. Hopefully we'll fix this. Back to Melanie.
Yay, great, thanks. Okay, so yeah, all of those examples are to say that it's really cool to focus our connection mojo on not individuals isolation, but their connection, they're the squishy stuff. So my approach, and again, this is a technical talk, so we sort of technique agnostic design folks started. So the design is kind of composed of the 4 different areas: structure, dramatic, emotional desires between characters based on those dramatic, and then how the relation. So again, technique independent, but if you're curious, I've been using ASP for generation. Thanks, Adam, for laying that background a bit. And also Ensemble for simulation of action. Ensemble is an engine developed here, coming out of the Prom Week sort of legacy. If you follow me on Twitter, you'll sort of find out when that's officially released and has documentation. Definitely proud of it. But it's not. So let's start with structure. So this is the most low-hanging of relationship graph. The more formal societal forced relationships, like family, employment, it's really domain specific. So you might not be using it in modern society, medieval society, whatnot, project. So it's what most generative social systems already do. Some well, bad news does generate. It knows your immediate relative set. And that's what I sort of started with, writing social project. But it turns out that it's really boring. I think I see it as a foundation, fuzzy obligation, power dynamics, those are taken out of this structure. The next one is dramatic tools, which is inspired very directly by Robin Law's drama system, which is an RPG, tabletop role-playing system for focusing on dramatic, focused on rather than heavy. So this is from that manual. During character creation, you're generating dramatic. But my here is to say I do it using rule-based system. So driving any compelling dramatic character in. So that's like what your individual character is sort of at war against themselves. I like the last point they have here. In many cases, you can your dramatic pull as your desire. But on the other, the character trait that makes it least likely. So it's like you are your own worst enemy. And that can manifest in a lot of the webcam is blocking. So related story value. See that concept described in the book, and also for character. Story values are from narrative practice work, and they're also about those. So here are selfish, altruistic, subservient, self, have like versus isolation, connection. So based off of have desires that this is also now bring your dramatic specific by the other. Example, a character wants a father, love from mother. These examples are super rooted in the whole RPG setting, but I think there are a lot more ones inspired by our new non-interactive. And then the tension in those arise with the other player that you're sort of targeting is withholding that desire or opposing that desire. So for this first example, a father character would say, I withhold because I want you to be private. I want love from someone. I can never love you as I should have because you're born a brother. That's so it's kind of like these really sort of rooted opposition between the starting of relationship graph between people on some. The last one, how relationships change over time, is inspired a little bit by this kind of odd paper called Balance Theory and Other Extra Balance Properties applications. And it's sort of this application of a sort of graph theory applied to library analysis. So they analyze fairy tales like in terms of the graphs between characters and those graphs balance if the tensions between characters. So this one actually every little graph here. Should we like no more time? But I'm wondering, like, should I just wrap up really quick, or should I just
wrap up.
Okay, cool. So yeah, it's kind of like using graph theory to inspire how you can use a narratively written graph, alter based on that. So yeah, that's my proposal to programmers. The squishy stuff between characters is narration and also so
yeah, you can do some questions. I'm gonna take a look at things while you do that.
Are you
exactly, yeah. So a lot of the ensemble cast, but have a lot of ability that so yeah, the graph sort of focused around a protagonist or an ensemble of protagonists. Great, thank you.
All right, we're going to take a quick 15-minute break. Hopefully, after that, all the audio issues will be resolved, but see you in 15.
Okay, welcome back everyone to Generative Methods Day. We have just returned from our break and are now ready for the second group of 4 talks. So again, for those of you who are just joining in, the whole idea here is in honor of Procedural Content Jam. We decided here at UC Santa Cruz to put together a series of talks highlighting the kind of generative methods work that we do here to give you a flavor of what research in generative methods is like, and perhaps inspire you to perhaps want to do this for yourself for full time. And one way to get into generative methods full time is to pursue graduate study. And I'll add my second and final plug here, which is, we are accepting applications right now for our Computational Media Master's and PhD program for starting in fall 2018. Anyway, welcome back, and the first talk in the second session here is by Kate Compton. So Kate, take it away.
Just slide over. Good to go? There we go.
All right, thank you for the introduction. I prepared 30 minutes of slides because I thought it was a 30-minute talk. It's 12, so prepare for a roller coaster. So my talk is called, I am actually giving a slightly different talk than I had pitched. It's called The Future is Baroque, and it's about how generative art is going to change the way that we think the future is going to look. And so fabrication, when we think of fabrication, we often think of sort of an industrial environment where large numbers of people are working to build a single object, but many, many instances of that object, they're all going to be identical. So like the Henry Ford assembly line. But now fabrication has turned out to mean something different, where we have all this fab at home movement with 3D printers, laser cutters, CNC sewing machines that are allowing us to create different things, sort of not one thing for 100,000 people, but 100,000 different things for 100,000 people. The nice thing is this isn't actually a totally current movement. We've seen things like laser printers and old-fashioned printers in the 1980s be used to make everything from magnet kits to personal to family letters. And I really wanted this when I was a kid. This is the Barbie Fashion Designer CD-ROM. This is an interesting sort of at-home manufacture kit where you design on a simulator clothes for Barbie, and then you can print them out on an inkjet printer. But yeah, we're seeing all sorts of devices from like laser cutters to fabric printing through Spoonflower, which is you can design fabric and then get it printed. Even things like shoe editors are available online now. So it kind of stretches from being able to design anything you want to being able to make small edits on existing products. So you can change the colors of your Converse, or you can set up different kinds of heels. And we're seeing a sort of aesthetic start forming out of this. So these are products which have been designed to be 3D printed. And 3D printing gives you a different aesthetic because it doesn't have some of the conditions of previous forms of manufacture. So we see things like this doorknob. You can have squid rings or objects that are just not physically manufacturable. So the question for this talk is really, what does the future look like? So we've seen ideas of what the future looks like from Star Trek. As you can see, there's no texture on anything. Everything is sort of matte black or shiny black. And then even when you get to Star Wars, where there's texture on things, it's texture that is sort of unintentional, purely mechanical. It's designed to, like, these are constructed obviously, but they're constructed to look like an HVAC system that had no thought put into its design. And this even seeps into our perspectives of what we think the future ought to look like and what we think people who are the future ought to look like. So this is Steve Jobs sitting in Steve Jobs' apartment, which famously has no chairs. And he has one lamp and a couple of books and a record player. And this is what the future ought to look like. The future is not full of decorations. And then it seeps into our sci-fi. So when you look for future cities on Google image search, you see all these sort of sleek, futuristic buildings with no ornamentation. And I think there's different pictures of the future. So what does the future look like? Some of you may recognize this image. This is from Firefly, a show which takes place in the future. But I liked it because it kept a perspective on what does the future look like well, whatever it is, it's going to be guided by the sort of desires that have shaped the way our worlds have looked like for the past, 3,000 years of human manufacture. There are still patterns. There are still fabrics. There are still ruffles that are not strictly mechanically purposeful. She has a quilt. This is so far the only example I've seen of a quilt in sci-fi. We've made quilts for thousands of years. Would we stop making quilts? Would we stop having patterns? We've had pattern carpets for thousands of years. Why does suddenly Star Trek, there are no patterns on our floors? Maybe the previous 3,000 years were an error, and sometime in the 1960s, we've correctly surmised that floors should not have patterns. Or is that the glitch? So my argument here is that 3D printing is going to cause the fall of the modernist aesthetic. I'm sorry, Jim. Or it's going to cause the fall of it as the default. So briefly, the argument that I'm going to make here, because I don't have a lot of time, is that a 3D printer is largely like a raster printer, where the head prints in 2 dimensions. So many of us have seen a raster printer in operations, and we know approximately how it works. And if you've bought ink, you can look at this and say, which costs more to print, this big black rectangle or the origin of species? And we know that the big black rectangle costs more to print. And we can also say which costs more to design, the big black rectangle or this Dürer print. And we kind of know which one costs more to design. So it's going to cost me more time or effort or money to design the one on the right than the one on the left, but it's going to be cheaper to print out the one on the right. And so you can kind of think of 3D printers in this way. 3D printers are not going to optimize for big black rectangles. So yeah, warning, very brief architectural history. I apologize to the people in the room who have already seen this part of the talk, but I'm fond of it. So yeah, this is the Doge's Palace in Venice. You can see that there's a bunch of different marble columns here, and they all have different carvings on the top. Here's another picture of an even more Baroque column, and this has an entire story going around the top. So each side of this column, this column is different from all other columns. Each side of this column is different from all the other sides of this column. And so I'd like you to think, what is the price for building this thing? This is the Doge's Palace. Well, it kind of breaks down like this. You have labor for materials, labor for construction, and labor for design. So labor for materials is getting the marble out of the ground and hauling it from Turkey, where most of the marble came from, all the way to Venice, 1,000 miles away. Labor for construction is taking that block of marble, honing it down into a column, carving all the little fiddly bits around on the top, and then putting a roof on it. And the labor for design is just sketching out which story should we put around the top, where should the horses go, what do people's faces look like. And it's interesting because it breaks, it sets up the material conditions like this. As long as we've dragged the marble 1,000 miles, and we've spent 100 hours carving it, we might as well have, some Renaissance artist spend another 100 hours designing each thing on the top. So we don't have a lot of raw material, but we've got all the time in the world. So decoration starts getting extremely optimized. And I'd like you to consider that this is a sensible outcome. As far as this dress can ever be called sensible, this dress is a sensible outcome of a specific set of material conditions. All right, so this is what it looks like. Suddenly concrete happens. Suddenly your labor for materials goes down to almost nil. You still have labor for construction, though, and this causes things like Gaudi's La Sagrada Familia not being built. You can get as much concrete for this building as you need, but it turns out actually putting that concrete into the shapes that he wanted, even with his design already existing, is an extremely non-trivial task. But it turns out you can solve that. So if you use flat-sided molds and don't have unique pieces, then labor for construction goes way, way down. And so it becomes this. We can build a lot. But, we shouldn't actually have to design anything anymore. And the less we design, the more the labor for construction goes down too. So all of a sudden, this starts looking really attractive. The official art history explanation for the modernist aesthetic is that after World War I, and I think World War II as well, the idea that this sort of Baroque, ornate, Greco-Roman style architecture was so linked to this horrible past that it just killed so many people that it was actually unconscionable to keep going architecturally in the same form. So you had to scrap everything and rebuild architecture from the ground up. So an economically optimal form of architecture becomes dominant worldwide. It was probably the compelling philosophy. So my argument is that the philosophical argument is probably a very small fig leaf for just this is an economically optimal way to proceed. So about 3D printing. It changes our costs again. So now materials actually decrease with complexity, if you remember those printed pages before. Something that is extremely fiddly and has tons of tiny holes in it is actually cheaper to produce than a big black rectangle. Cost of construction is constant with complexity, barring some support structures that you have to build, and the labor for design is the same old, same old. So if these two things cost the same, an IKEA table, which is sort of the optimum of we're going to make something that is as cheap to produce as humanly possible or mechanically possible, you get the one on the left. This is a quote from the Diamond Age, which is talking, so the Diamond Age is a futurist book where everything is 3D printed. And I like that he seems to have actually thought about this, and somebody has an exercise machine that is just like ornate as hell. Sorry, I shouldn't swear on stream. It is extremely ornate, and it has like nymphs and caryatids, which are people-shaped columns, and each one is different, and each muscle is individually sculpted. And I like to call this the Bowflex. Cheesy. So yeah, if we have this kind of equation here, don't care for materials, don't care for construction, we still have labor for designs, like somebody actually has to spend time modeling chair dragons. That's going to be a different condition. But how do we solve for this last one if the only thing standing in our way from the chair on the right, which I really want, I think people should be able to get the chair on the left, but they shouldn't have to get the chair on the left, is design tools. And our design tools are currently set up to build cubes. So the tools we have are designed for cubes. What are the right tools for 3D printing? We're going to leave behind the old picture of the future and end up looking something that is often more biological. So generativity is kind of design without designing. There's still design in it, but less than we thought. This is a previous pitch for my cards that I use. So there's techniques like tensegrity simulation, where you can model extremely complex shapes that are manufacturable using new techniques easier. Similarly, tensile membranes. These are things where it's easier to use a computer to design these things and use a computer to cut out the pieces of fabric to your precise specifications than it is to make a cube. Things like Grasshopper 3D, other sorts of interesting emergent modeling softwares. Bathsheba Grossman of Santa Cruz Local makes really fantastic stuff with surface tension and metaballs. You can even make stuff with strange attractors. They're a little too chaotic to be used for maybe chair design, but this is something where you have used a mathematical tool that you have very little control over to design something that you could not yourself design. Nervous system designs 3D printed dresses and they have a separate system such that you can compress the modeled dress into a ball mathematically, 3D printed as a very small bundle, and when it's finished 3D printing, grab a corner and the dress falls out, which I think is pretty fabulous. I tend to design a lot of stuff with particles. So on the bottom right is, I don't actually need the sound on this, but is a 3D printable snowflake maker that I designed using particle systems. I also make a lot of stuff out of grammars, which are things made out of things, and being able to, so there's a language I wrote called tracery that many people in this room and possibly on the stream are familiar with, but that allows you to structure how to make things out of other things. I haven't seen this used much for modeling, except that there's a project called Shiv Integer, which uses Thingiverse models and a grammar to construct bizarre new objects, and they've actually had a gallery show that I'm quite jealous of. Parametric methods are a personal favorite of mine. These are some textures that I made with parametric generators, and I actually have manufactured these. There's a t-shirt shop that you can buy t-shirts at. I've made skirts with this and actually manufactured that skirt. I'm currently working on taking these parametric methods and turning them into a genetic algorithm so I can have a pattern that I like. So it's like, how do you design without designing, and how do you then bring some control back in? So having parametric methods that I can then sort of move through this possibility space. This possibility space is actually rather too large for me to move rationally. So I had this n-dimensional space. You can kind of think of the DNA that creates each of these patterns is an array of floats. So I have a little representation of my DNA down there, which nobody on the stream can see, but it's just an array of floats. This is interestingly modelable as an n-dimensional cube. If you have an n-dimensional cube, I'm a very physicalized person, I think spatially very easily, and I think a lot of people do as well. we can take this n-dimensional space and do a lot of really interesting things with it. So often in these, you will have a sort of DNA representation, this array of floats, and through a variety of generative methods, you will construct some sort of individual. This is kind of like having a seed's DNA and then eventually growing that through whatever interesting biochemical methods into a plant. I've made lots of plant generators, so these are a bunch of plants made with this DNA that grow into very different trees. This is the same slide again. Okay, so you have n-dimensional space. It's really hard to visualize that. This is, I think, somebody trying to visualize 4-dimensional space. The plants and the stuff that I've generated tends to have anywhere from 20 to about 100-dimensional space. There's nothing rationally that you can do to visualize that. But you can at least think of each element in this as a different vector in this space. So if I have 3 fairly different flowers, they should be kind of at 3 very different locations in this n-dimensional cube. But I'm still inside of a cube. And I can say things like, this flower is closer to this other flower. You can still calculate distance in n dimensions. But once you have this n-dimensional space and we can't visualize it, can you at least map it in some sort of sensible way? Even if it's just an approximation, as all maps are, can you suggest ways for people to understand the space? So we've seen things like Gillian Smith's analysis of expressive range of a level generator, and then Michael Cook has taken that work and moved it further so that you can have a parametric I don't know if it's just for parametric or if it's for all. I think it's just analyzing the output, not the input. But you can at least still kind of map your generative space. So I've generated a bunch of stuff. Give me an approximated map that is perhaps useful. You can also move through possibility space. Remember how I said this is kind of physical? You can draw curves in n dimensions. If I have a space where things that are close physically are also close in their output. So I have, if I make a flower with one form of DNA and I waggle the DNA a little bit, I should get a flower that is similar, not a flower that is completely different. This is kind of the smoothness or the locality of the space. And if you draw a curve through that n-dimensional space, it turns out you can use Bezier curves in n dimensions, and that's pretty fun. You get animation. So this is a procedural animation I did of the flower generator evolving. So what this is just, this isn't even with curves, it's just pick a space, move slightly. It's a drunkard's walk algorithm, essentially. So do a drunkard's walk through n dimensions and draw me the flowers. And you can see they kind of, this is not a particularly continuous example, but they do move mostly continuously. Depending on your parametric space, you can actually have things that move much more smoothly and feel like an animation. You can have genetic algorithms where you sample, sorry about the font spacing issues. You can have genetic algorithms where you are sampling near the space, like you have a point, you sample near that space, you pick the best one, and you kind of iterate through there. So you can use this spatialization approach, or like spatialization idea of thinking, to say like things that are nearby are good, some of the things are better than others. This works great if you can actually have a mechanical way of saying what goodness is, but for design, often we don't. So there's also different ways of annotating possibility space. This is a paper that creates landmarks within a possibility space of trees. So now instead of kind of floating this n-dimensional possibility space, I say, how far am I from an oak tree? How far am I from a pine tree? Am I currently on the line from oak tree to pine tree, or am I moving closer to cactus? So this actually works well. You can also say, like, there are regions in this space. And so this is a project where they regionized the space, found sort of the landmark in the center of each, or created a landmark in the center of each region, and then judged you based on which regions you had visited or not visited. So I like that this is kind of similar to the way we understand physical space. There's a book called Image of the City, which is about how we understand cities. And they say that we need things like paths, edges, districts, nodes, landmarks to understand the space that we live in. And so we've seen in these past 2 projects that we actually have landmarks and nodes. We have paths that we can move along, or we can be off the path. We can have districts and edges. We can have, I could be in a district or not in a district. I can have districts that I can't get to yet. And I can start understanding this completely ununderstandable space in a more intuitive way for me as a human. You can even say, like, there are parts of this space that unfold into other parametric spaces. So, maybe they're unlockable somewhere. You can also think about, like, what gets used to create this DNA. I can have DNA or I can set the DNA for something. So this is some parametric dancers that I've created, where you can. All right, we'll do music. Cool. So I'll wrap it up. But this is you can use music to set the parameters. You can use words. This is some pronunciation to vec stuff. So you could annotate a text with generative trees. You could do interesting forms of input. You could even use maps. So if you wanted to make a Pokemon Go, where each point on a map mapped to some interesting piece of generative content. So like we're currently in the Rose region, and I want to go to Spain so I can see daisies. And I'm doing fabric stuff, which is fun. And oh well. So much for animated GIFs. I think my presentation is timing out. Anyway, I'm really hoping that I can make something that's navigating n-dimensional address space kind of in the same way that you would navigate the matrix. So yeah, what does the future look like? I don't know. It might be smooth shapes. It might be Baroque. It might be an interesting mixture. So thank you. Any questions?
Yeah. Chat brought up a point while you were bringing up design tools basically make cubes. How would you speak to things like ZBrush or that, I don't think it's an Oculus game, but where you actually have
the Oculus Medium.
Yeah, where you have sort of two things. Do you think that maybe one of the other futures is not that we all go through generative methods to make stuff, but instead we just get more and more control over what we want to make?
So it's interesting you bring up Oculus Medium. Because that and Tilt Brush are actually using an extraordinary number of generative methods to take my gesture. So if you imagine the gesture that I make through space, and that's really just an array of points. And they're taking that array of points and they're building so in Medium, I believe it's metaballs that are getting extruded along. So similar to the construction of the creatures in the Sport Creature Creator. And they're doing lots of stuff with that. So that's amplifying my action through generative methods. And I guess a lot of the point of this talk was your generative methods or your lack thereof are going to shape how your output looks like. And so Oculus Medium stuff has a very particular look to it. Tilt Brush, which is a very similar thing of let's take my 3D positional stroke and annotate in some way, does so with sort of extruded textures, flat textures, and it has a very different look. So both Oculus Medium and Tilt Brush have 3D shapes that look entirely different from anything that's been created before and look very different from each other. And so you can see very much the thumbprint of the material and the thumbprint of the genetic algorithm, even when two artists use the same tool.
Okay.
Thank you.
Right, thank you.
All right, it is time for our next talk. Where is this one? Yes. Cool. So take it away, Afshin.
Sure. Hi, my name's Afshin. I'm going to talk about generated levels and generated games. This is my project called Garland. And I guess let's start. So, there are plenty, and I mean plenty of procedural level generation algorithms. We've seen them in different games. We have Infinite Mario, and it's a plethora of generators. Recently, we've seen AI Birds having what's the same level generation competition. So, but this is in the academic world. Even in the industry, in gaming communities, we've seen different kinds of procedural generation algorithms. For example, we have No Man's Sky, a game that is known for all the hype about procedurally generating planets and an entire universe and life forms and so on. But we even have community projects like Oblige is a level generator for Doom that has existed for plenty of years. So we know that there's plenty of these procedural level generation algorithms. But the problem with them is that they are game specific. They are only reactive to the rules and assumptions of one very specific game. So be it Doom, be it Angry Birds, or be it No Man's Sky, the algorithms only respond to one game. But procedural generation is not only about levels. You can design almost anything. For example, you can design games. For example, we have systems such as Game-O-Matic that take more conceptual representations of a game and turns them into smaller game mechanics. We have board games such as Yabla, made by Ludai, a system by Cameron Brown that can create board games. We have the Angelina series that creates arcade-type games, and even puzzle script generation. So one of the problems with this is that there is not really a good level of interaction between level design and game rule design. So we want to explore this. And finally, we have generalized level generators. Generalized level generators try to take the assumptions of games out of the loop and create level generators that are responsive to almost any given game. In this case, these are the examples of a level generator made for VGDL games. They take an input representation of an arbitrary game, and with game I mean a video game of the grid physics type. And then based on the knowledge gathered from the game, it starts generating levels. In this case, the knowledge it gathers is what types of tiles are traversable and which ones are not. And we end up with these levels that are very generic looking and sometimes even random looking, that don't really respond to like all the nuances of game design. It only knows like where you can go, where you can't go, and what kind of tiles you can place. And this doesn't really reflect the qualities of a generated game. So if we look at the generative space of procedural generation in games, we have plenty of systems that have been made. And we can divide this into like three bigger, smaller spaces: aesthetics, spaces, and rules. So we have systems that design rules like Variations Forever, VGDL generators, the Angelina series. We have level generators, and they all interact at some point in this space. So for example, we see rules taken by AGD systems, aesthetics, like you can see all these asset generators that have been happening throughout the years. But what we want to explore is this space here, really see what we can generate by exploring the intersection between rule design and level design. This leads us to interesting research questions. So can we create a system that can generate levels that conform to the rule features of a generated rule set? And this comes with its own challenges. We want to see if we have problems with its knowledge representation. We want to understand what knowledge representation best encodes games. And with games, I'm going to limit it to 2D arcade games. There's plenty of different games that can be generated. And in this system, we are focusing only on 2D arcade games. So that's our definition of a game, quote unquote. But games can be much more than that. And we also want to encode levels. So this is like a very important knowledge representation issue that we want to deal with, in addition to what generative techniques can help us achieve this objective. And there's plenty of different techniques. We have search-based approaches, we have constructive approaches, etc., etc. So with this, without further ado, we present Garland. Garland is a system that can generate both rules and levels as a single artifact. And what we did is to create this pipeline architecture that takes no input, and then we start generating games. So we generate a rule set, and we'll explain the generation process in a bit. We evaluate them, and then we select the level generation strategy to further generate levels, and then we just like wrap it up into a neat little package and output a game. So how do we encode games? And games, again, this is my definition. We're just focusing on the 2D arcade space, and like we want to encode games as a series of features. And what are features? Like, what are these characteristics that define games? For example, we want to define what the game world is. For example, in terms of physics, we want to know what the gravity in the game world is, what the moving speed for players are, what's the maximum velocity they can reach when they're falling in this space. But we also want to understand what players are doing, and we want to give a space of affordances, like, can you jump in the game? Can you shoot projectiles? Can you interact with things? In addition, we want to capture the goals. What is the objective of the player when they're playing games? So we want to encode things such as goals. So we decide to focus on a small discrete space here, and we collect the 3 goals. For example, like, do you have to move to X, Y? Do you have to collect at least X items? Do you have to eliminate at least X enemies? these are goals of a game that we wanted to encode in this generative space. And in addition, we added like some kinds of enemies that are not completely generatable. But we also wanted to add like what kinds of NPCs you can interact in the game. So with this, we decided to encode all these features, and we added like some values to some of them. Like we decided to like constrain the physics world between a certain number of values, and we create vectors. So you can see, like for example, we encode things like how fast can you move, if you can jump, if you can shoot, etc., etc. So how do we generate it? Like this is like a simple process that we decided, like if we have no input, like there's two ways of doing it. And there's interesting ways of exploring this design space, but we can deal with that later. For example, we can start with random generation. We can just randomly sample anything in the design space and just hope for the best. And that's where evaluation comes in, when we want to prune all these like bad combinations of parameters. Or we can take assumptions about what we know about games already and use them to explore like a very specific subset of a generated game. For example, if you see a game like Mario, we know that you can jump in the game, that you have to reach an exit goal, so we know these assumptions are fixed in this generated space. So we make these assumptions and then start exploring the variations on the other parameters for the design space of Mario. And so we are going to skip the evaluation part because it's not really relevant to the story of this generative system. And now we want to talk about like how do we select generators, assuming we already validated our rules and we have a simple machine learning classifier that like just prunes this space for us. How do we select the low generator? I mean, we encoded like a series of like rules about game design, and what we do is like we just run through the vectors, analyze the features, and basically kind of like a decision tree. We just choose what generator fits the best. So we have Mario type generation, R type level type generation, contour level generation, etc., etc. So with that, when we choose a generative strategy, then we generate the levels. So how do we encode levels? And to encode levels, we just basically take the notion of design elements by Sorensen and Pasquier. And what design elements are basically the most unitary single thingies that comprise level. So for example, in Mario, you have like blocks, you have pipes, you have Goombas. These are examples of design elements. In R-Type, you have turrets, you have other spaceships, you have the base terrain. And these are like the unitary elements that comprise any level design in each game. So in this sense, we want to encode design elements as a series of parameterizable geometry pieces that we can place inside a level. So we determined that we needed like some parameters to work on. So for example, we want to make pieces that are parameterizable over Euclidean space. We want them to like be able to expand or contract in Euclidean space, and so we decided to encode things like stairs, platforms, parallel things, mountains, etc., etc. Wow, we're running out of time. So, so how do we create levels? And level generators in this system are highly parametric. So what we do is like we can do a division of space over passes and chunks. So if you can see, like these would be like the regions we subdivide the space in. And then we also add assumptions about physics and design elements. So quick parameterizable range. This is an example of how some different parameters work. Mario just does bottom and middle passes. And we only have like a full range of allowed design elements. And as you can see, like the levels definitely start looking different because they do different passes. For example, the two bottom generators work on passes on the top, whereas the first one doesn't. So we can definitely generate more generators by using these types of definitions on whether they can work in different passes, different regions, and what design elements are allowed. So we set physics assumptions first when we are generating levels. So we already have like an encoding of the rules, and we want to like know how the spacing works in relationship to like the physical constraints of the world. We already know that like the physical characteristics of the world. We know gravity values. We know like terminal velocity values. So we know we can calculate how to space platforms, and then we divide the spaces over chunks and passes to know which regions we need to fill at a time, and then we start filling them with our allowed design elements. Here's some samples of what the levels can look like in this system. And how about we show some games? So this is how the system looks in action. For example, this is a counter-type game that we were able to generate. What's with video? So for example, in this case, we have levels that work on 3 passes. We have the affordances of shooting, kind of like an action-type game. If we fast forward a little bit, because I guess we're running out of time, we have more games, but I think this is taking too long. So let's just wrap it up real quick. We developed Garland. This is a system that can generate both games and levels. We have started an exploration of the design space between rules and levels, and this is definitely an interesting space to explore. But we can go deeper. Like, our space is still too constrained, so we want to identify new features that can define more games and go beyond like 2D arcade style games that have like more than one continuous screen. We want to explore things like camera relationships. We want to explore things like physical interactions, etc., etc. Well, we're running out of time, so thank you. Any questions?
I'd like to field a quick question from chat. Have you published this anywhere?
Yes, no. So it's in review.
Where is it in review?
Transactions for Computational Intelligence in Games.
Great.
I have a quick question, if you don't mind. You mentioned that last game, that last level
Yes.
had some affordances. Are those affordances themselves generated, or are those kind of are those rules that get?
So the affordances in the game are basically encoded as part of our knowledge representation. We have 2 affordances for agents right now, which are shooting and jumping. But we plan to expand the generation of affordances by defining a parametric model of like what you can do by interacting with the world in terms of physics.
You think an affordance, I guess, the way you're defining it requires that you have some action that makes sense in the space.
Yeah.
And if you were generating affordances, they may not be nameable. And what would that mean exactly? It's just a thought. That's from my head.
Can you repeat the question?
No, I'm just thinking about this idea of affordance as opposed to a design element. The affordance kind of emerges from what design elements are.
Yes, so we want to explore the appearance of emergent gameplay in our generated games by understanding, for example, the creation of new design elements. For example, we want to create design elements that react to, for example, physics. So for example, if we want to create a bouncy tile, what kind of new affordances does that release? If we make tiles that, like, if you touch them and you just, like, it changes the gravity values in our game, then that definitely leads to interesting emergent gameplay. And what we want to do is, for example, in the future, would be interesting to plug in testing agents, for example, simple general game playing agents, and we can look at the general video game AI competition as a reference for them and see what emerging gameplay leads by just analyzing the game traces over simulations.
Cool. All right, thank you.
All right.
So I'm in 2 places at once. Literally 2 different times.
I got you, fam.
Thank you.
Oh, well, this is going to be easy for me because I don't have to go anywhere this time because I'm the one who's talking. Thank God, speaker notes. Okay. So, hi everyone. In case I forgot to introduce myself earlier, I'm Joe Mazika. I'm yet another PhD student here at UC Santa Cruz, working under Jim Whitehead. That appears to be a fairly common refrain. It's almost like he put this together or something. So, procedural generation is the art and science of making programs that make things. And having a generator that can generate things in different styles helps make a generator stronger. This is basically one of the pillars that I'm resting my dissertation on. So please, chat, don't tell me I'm wrong yet. Wait till Jim signs my dissertation, then tell me. So what is style? Style is kind of a contentious topic in the art world. But instead of diving too deep into that theory, because let's face it, there's a lot of theory, there's a lot of ink on this topic, let's focus on a definition that we can use to actually build these generative artifacts. So I'm saying that style is the space of common features that a set of related creative artifacts share. So in order to generate things in different styles, we need to specify what those different features are. This definition might seem a little simplistic and maybe a little broad, but it's definitely really useful. For instance, what we have here is the world generated in a style resembling the artist Mondrian. So why use style? Well, there's two major aspects that I see immediately that are useful. First and foremost, you can help tailor and tune the particular aspects of the artifact so that if you generate something in a style, you know it's going to have features X, Y, and Z. Well, why would you want to do this? Well, for instance, let's say you're making a game, like I know a lot of you jammers are, and you want to create a sense of progression and difference. And what we have here is a level from Spelunky, a game that famously does a lot of generative levels, and this is one of the levels from the opening of the game, but as you progress through the game, suddenly you're in levels that look like this, and they're really different from each other, and it helps show the player that you've moved from one stage of the game to the next. And after this, I think there's like ice caves and then like some weird, almost futuristic-y. It's been a while since I've played Spelunky, but nevertheless, there are reasons for wanting to think about this. So the different kinds of generative methods that you incorporate into your process will require different sorts of techniques for embedding style. And so some of these things are going to tie into things that people previously have mentioned all throughout today. But I'm just going to be covering 4 different techniques and the ways that I see style incorporated into those. And hopefully you'll have some takeaways that you can use to make your generator a little more cool. Bear in mind, this is a 10-minute talk. I'm going to be shooting information out of a fire hose at you, but poke me on Twitter. If you're following the hashtag Generative Methods Day, I've been posting a lot there. The other person is mostly Jonathan, but don't worry about that. And my Twitter handle will be at the end. So first and foremost, grammars. Grammars are a simple but powerful way to generate a lot of content quickly. There are many different kinds of grammar, but in general they work by taking a series of rules that take symbolic references and fixed outputs to randomly construct organized outputs. What we have here is an example grammar from Kate Compton's Crystal Code Palace, which is her tutorial website for her grammar language tracery. And so you can see we've got these JSON-like structures that get run through a system to produce different kinds of sentences by combining the different words in different interesting ways. Of course, what we can do in text, we can also do with shapes and images. Pictured here is a section of rules from a 1981 paper on designing a shape grammar for houses in a style reminiscent of Frank Lloyd Wright. The issue we face with this particular system is that the rules for generating these houses are so intertwined into the rules for the style that trying to build a different style into this grammar would require rebuilding this from the ground up. So that is one thing to be careful of. The best way to work around that is to have a separate section of style rules that get incorporated into your grammar and just hot swap things in and out. Next, we have genetic algorithms. Like Kate was talking about, genetic algorithms allow us to explore a space, but you really need some kind of evaluatable fitness function that you can hill climb towards. So a really simple way of encoding style would be to say, okay, the closer I am to the style, the better my fitness function for my genetic algorithm scores. The issue with that, of course, is that you have to have some way of computing that number. For some of the more esoteric and hard to really grasp styles, this can be a little complicated, but if you're trying to make things that resemble the curves of a Coke bottle, those can be mathematically defined. Or if you're saying my Mondrian style is having this number of lines and this number of squares filled in red and blue and yellow, that can be something you can build towards. And of course, this wouldn't be a talk in 2017 about style without mentioning that we've got a lot of cool stuff with neural networks. Specifically, this is the original style transfer paper by Gaddis et al. They've got really cool results, but they kind of tend to be their own end rather than a means towards an end. There is a lot of ongoing academic work in that area, and a lot of really good open source implementations of these that you can pull down and play with on your own. And they do look really cool, but I would be interested in hearing how people take these results and build them back into other things, such as interactive experiences. And of course, finally, we have the stuff I use, which is constraint solving. So I use ASP, or answer set programming. Isaac mentioned ASP in the very first talk of the day, so feel free to pause this video, go back, watch this, and catch back up. Specifically, I use Klingo, produced by the Potasco Group, and how this works is you describe the space of all possible worlds using a prologue-like syntax, and then you also include constraints to remove any parts of that space that you don't actually want to appear in the output. I specifically am using answer set programming to generate Lego models, such as the ones you see here. Or I guess here, if you're looking at this in the stream. So how I do this is I encode the model itself and the style as a series of facts and rules as part of the answer set programming paradigm, and then use those to generate a sketch first. This sketch isn't the final model, but rather like the bounding box for where all of the different Lego pieces are actually going to be. This is due to some computational complexity issues with trying to just go straight to the bricks. After that, I do that second pass to actually get all of the bricks laid out. And yeah, so there are a lot of really interesting generative methods out there. Style is a really interesting and powerful way to make your generator do more interesting things with just as much as it's already doing. If you have any questions about it, feel free to email me or message me on Twitter. I've also provided a link to my GitHub page for my Lego work. And if there are any questions, wow, I went fast.
Nothing from chat.
Okay.
I'll front you a question.
Sure.
How, like, well, this is totally loaded.
Go for it.
We work in the same research group, and I've talked with Joe about research a lot.
Hit me with your loaded question, person I've never met before.
How do you, so Lego bricks are complicated and have lots of little knobby bits and stuff. Can you encode all that in ASP, or do you have more trouble with sort of particularly bizarrely shaped bricks?
Yeah, so the question is, Lego bricks are weirdly shaped. Do you have trouble doing that in answer set programming? And the answer is yes and no. Yes, you know, because answer set programming by itself only cares about discrete values, you can't actually model a continuous space. which you would think would be really good for Lego bricks because they're all very uniformly sized. On the other side of the coin, there are all the weird decorative-y bits. But my current trick for that, and this hopefully won't bite me in the butt too soon, is to just kind of use the fact that I'm generating these bounding boxes to kind of abstract that out, and then have rules for, well, if there aren't the actual Lego knobs on top of the particular piece I'm dealing with, you can't actually attach something on top there and have restrictions in that way.
Cool. I actually do have a question from chat too.
Okay.
Do you have examples from your Lego work in solving the same problem in different styles?
Yes, but I forgot to put that in the slide deck because I am bad.
Is it on a GitHub page?
I think so, but I will have to check.
Great. Thank you.
Yeah. Yes, no, the GitHub page has both a default style and a pirate style that you can pull from.
Okay, thank you very much.
Yeah. And since I'm already up here, that means I can set us up for our last speaker of the day. The secret MVP of the stream.
let's not throw on terms like that.
Take it away.
Hi. Hello. Thank you very much for inviting me to talk as part of #Generative Methods Day. It wouldn't be a Santa Cruz event if we didn't take something that is known by a different hashtag on Twitter, PCG, and then rename it. We're very good at names in Santa Cruz. My name is Jonathan Pagnuti. I am a researcher here at Santa Cruz, and I work in the Augmented Design Lab, which is mostly affiliated with sort of generative methods. It's a lot of what we do in all kinds of domains. You've heard from people in my lab generating games, generating surprises in games, to generating Lego models, to, and now my talk, which will be generating food. That's a little misnomer. I'm generating recipes. I'm helping you make something to make I'm making something that makes something to help you figure out what you're going to make for dinner. I think a big sort of theme to take away as somebody who has sat in the room and listened to all the talks today is that understanding is hard and generation is easy. And that's a massive oversimplification and a trivialization of exactly how much work goes into actually producing a generative method. But I think a lot of what we do as researchers is try to understand a domain well enough to be able to make a generative method around it. That's everything from Kate's work in trying to figure out how people sort of use generative methods in just about every context because she's a wonderful researcher, to my own work, which is about food. So I'm going to spend the first part of this talk mainly focusing on what even a food is, and then we'll get into other stuff. I'm primarily known for my cocktail generation research, and by known, I mean infamous. The top two are from an older system. The bottom one is from a more recent one. That's why it's in a different color. I kept the same naming scheme, which is always adjective plus animal name, which will get you so far in naming inanimate objects. It turns out that's wonderful. I stole that from Kate, who presented earlier, and I will always use it forever because it's really simple, really easy, and adds a ton of personality without really trying. And I want to motivate my primary research question, which is the same question that so many people have to answer every day. What the heck is for dinner? And how do we use a computer to help us come up with what's for dinner? I'm going to talk about how I talk a lot of things. It means I'm going to use examples from classic art to sort of flesh out this question and show why it's complicated. Although I'm pretty sure as a human being, you have dealt with this and understand it pretty well. Some of the things we figure out when we're trying to figure out what's for dinner is if something tastes good. This is Adrian Bauer's The Bitter Potion, and it's a bitter potion, and this person is not having any of it. That is probably not what's for dinner. Other things we think about are hunger. Are we just hungry? Do we not even care? Do we just want satiation? We need the calories. And to illustrate that point, this is Christian Kohn-Krump's Struggle for Existence. Is it a tradition? Are we eating a meal because it's important? There's a social context or a social responsibility or a set of symbols that we want to invoke that mean something to us, deeply. The picture I'm picking for this is of Thanksgiving. It's Jean-Louis Jerome Ferry's The First Thanksgiving, which is something of a mythical thing in the United States. Thanksgiving didn't go down this way. It didn't look like this. We have the historical records. This is fake. This is a lie.
but it means something to us, and it's important to us, and it's part of our culture now, and it's, you know, a bit of who we are. Or do we think about things like cost? You know, this is Charles Wilde's The King's Eating Room, and it is somebody who probably doesn't have to think very much about cost. Or if they do think about cost, it's how much money can I spend, and I want to spend all of it. Rather than for some of us, we have to eat, you know, on a dime. We might not have that much. How can I get the most bang for my buck? So as I said earlier, I want to motivate and start this question off by trying to figure out how can we help computers understand what food even is before we can think about generating stuff. This is a cover of The New Yorker and one of my favorite pictures of all time, and will be in every talk I give from here on out, of a man describing an ice cream ontology, which is sort of a relationship. It's a graphical representation of relationships between various ice creams. It's also pretty accurate. I'd use that ontology. I think a computer could learn from that. That's solid. And a lot of this ties into something that Adam Somerville was talking about earlier. We can think about ontologies, which are sort of these graphic representations of which thing is the other thing, right? Each of these lines here in this graph say that this thing below it is a thing above it. So for example, an ice cream cone is a ice cream, and then a cone is part of an ice cream cone, and an ice cream cone with soft serve is an ice cream cone, which also is an ice cream. And Adam Somerville earlier brought up this idea of common sense reasoning, and how it's really hard to actually get computers to understand the things that we take for granted and we just know. He used something like 250 rules to encode sort of the common sense things that everybody just seems to immediately grok or know about games. And I do something similar for food. So my research has two primary components. I'm trying to answer the question, what's an ingredient? And how do we combine ingredients? And I'm going to spend a little bit more time to talk about how this is different from other things. Because you might say, well, surely we have to run into this problem every time we want to do anything. How is this different from, say, pictures? So when we have pictures, we already have a very strong and well-defined representation of what a color is that we can tell a computer. I'm using RGB space, which means I'm talking about sort of how much red, how much green, how much blue. That's like a known bad space for understanding color, but it works for this example. We already have sort of these numbers we can relate immediately to a color. We can tell a computer what a color is in 3 numbers. That's amazing. We can't do this for things like food, or particularly things like flavor. So if we want to tell how something tastes, we don't have this wonderful representation. Flavor is very unique from person to person, although there is some generalities between it, and we can do things like say it is likely that you will find lemons to be more sour than sugar. In fact, it's highly likely. Although if you've had perhaps a accident and your olfactory bulb has been harmed, you may not find this to be true because you have a different sense of smell and taste than the rest of us due to your tragic accident. There is no single sense that's truly responsible for flavor. The perception of flavor is a combination of the things you smell, the things that come in contact with your taste buds, the pain nerve that exists behind your nose. It's where your sense of astringency comes from, and that, I mean, sort of the bitterness, the thing that gets your lips to pucker, is actually a pain response. There's a wonderful field of nathosonics, which is all about sort of the sound that food makes when you bite it, and I love that. It's great. And furthermore, the language you use to describe these things can vary from person to person in sort of common parlance. Flavor scientists have much more regulated language, but when I talk about something having a musty flavor, that might not mean the same thing to me that it does to you, and I might have to use other words to help contextualize it, and we have to do this round of meaning swapping where you go, no, that's not true at all, and we kind of figure it out together. You can't do that with a computer. You can't negotiate with it because it's just going to do what it's going to do. So I borrow heavily from work from the IC Foods Consortium, as well as UC Davis, and use food ontologies to help me try to figure out, to define some language around food that is true to the computer. So at least the computer is internally consistent with itself. We might not agree with it, and there might be some interesting work. There's almost assuredly interesting work to be done about how do we negotiate this space together? What does that program look like? What are those UI, UX affordances? But that is not the subject of this talk. This is a generative methods talk, and I promise I will get to how to generate stuff in a bit. I use sort of this food ontology, which is, this is an advertisement for it, basically. And it has a bunch of different labels that I can apply to different food terms. This is all regularized language. All these things always mean the same thing. Most terms come with definitions. Foodon is an ongoing project. It's not entirely done yet. For example, the sort of food cooking processes are not completely labeled at all, and a lot of those things don't have definitions. Foodon also provides me with things like, oh, these two things are synonyms. If you're familiar with WordNet, that's basically Foodon for English. And WordNet is a sort of giant repository of things like synonyms and definitions and parts of speech of various words and hypernyms, which are ISO relationships between words. So red is a color, red is a hypernym of color. I think I had that right. I might have had that backwards. Don't at me. So this gives us sort of a basis for understanding what an ingredient is. But I want to bring back to the second point that I want to deal with, which is how do we combine ingredients? If we're going to generate stuff, we need to stitch these things together to come up with a new cohesive whole. And I use probabilistic soft logics in a slide that has too much text. Now, you've heard a lot about answer set programming, but I will briefly go back over it for the millionth time. It's essentially a way to do what we call declarative programming, which we start by declaring how things relate to each other and what the constraints are, and then we solve for various new facts that come out of those sorts of constraints and relationships, and then we sample that distribution. Probabilistic soft logics work exactly the same way with a twist. We declare I declare how ingredients relate to each other and various flavors with the same sort of basic logic programming syntax that if you've never done Prolog before is a little gnarly. It's very different from how you normally program, but it's really cool once it finally clicks. The twist on PSLs versus ASP is that I solve for how likely various things are, not for what they are. So for answer set programming, you have a nice on-off switch. This is true, this is not true. In PSL, we have a probability curve. This is likely to be true, this is unlikely to be true. If you want me to go into the technical specifications for how that happens, feel free to tweet me, and I will get into it. And then I sample the distributions, which matters more for PSL than it does for ASP, because things have different amounts of likelihood as our final solution to come up with a new recipe. I want to talk about how this is most recently lurked in my most recent system, which I entered in the computer cooking competition last year. Well, that was actually this year. It feels like last year, last academic year. This year, I did not win, unfortunately. But some of the other constraints around that system were that you had to use a very particular generation technique, which we refer to as, I'm sorry, I'm drawing a complete blank. It's case-based reasoning, which you essentially start with a set of recipes and then adapt them to fit a user query as your generation term. Don't come up with something out of the ether, instead take something that already exists and tweak it to fit whatever you need. So let's say a user desires an ingredient called pear syrup. We're going to set that to 1. That is highly likely because the user knows exactly what they want all the time. It's never been a problem. We then look through our database of recipes and we can recommend various ones based on relationships that we've defined between pear syrup. So in this case, things like eggnog were not recommended at all. If the user wants something that's like pear syrup, eggnog is very far away from any of the flavors that pear syrup might evoke or be similar to. But other sorts of more fruit-based cocktails are higher up. And interestingly, a gin cocktail, which I don't know if I'd agree with as a consumer of cocktails, but that's okay. And then we want to sort of take any highly recommended recipe and tweak it to definitely fit that. So we look at sort of how we can do swaps. In this case, we want to swap in apple juice because it's fairly close to pear syrup in a lot of important ways with other sorts of ingredients. You notice that there's some interesting things here. For example, swapping an apple juice for sour cream is considered 0 because sour cream never came up in a recommended recipe. There was no probability ever even assigned to sour cream being something that we were going to deal with, so we don't even bother generating swap rules for it. Well, we do bother. We assign them all probability of 0. This is an interesting time problem. We actually spend a lot of time sitting down and assigning 0 to things, which is a little sad. But for things like pear liqueur, which might be closer to pear syrup, we still think that apple juice is pretty similar to both these things and we're willing to swap in for it. Apple juice is a great swap for things like beer, which are fairly far away from pear syrup in flavor space. And so, with all of that being said, this is sort of my work and how I'm trying to help computers come up with new recipes. Thank you very much for your time. I think this space is incredible. It's fascinating. It's wonderful to work and try to design generative methods around things that aren't really digital. They're very physical. It leads to a lot of interesting problems. My website is up here. You can send me an email. It'll get moved to the best way to contact me is on Twitter, or that's it. You can check out some of my other work. All my papers are on my website. If you send me an email, I may see it. 50-50 chance. And thanks again.
Any questions from the
No. But I have a question.
Yeah.
Do you have any? Was one of the recipes from the earlier slide an example of what your PSL system has generated?
Yes, the last one. It's very similar to the other ones. It's still based around parts. It's why the background is different. Because parts are a great way for cocktails to... We all have an idea of what a part is for a cocktail, and it's a known way to measure out ingredients. And it's a known normalized way to measure out ingredients, which is very clutch. As we move on to other sorts of recipes, we need to find new ways to normalize. And ingredients generally either fall in by weight or by volume, and some things you can't measure certain ways. So you need to find interesting equivalencies as you move forward. Yeah?
What was the sort of deciding factor to do PSL rather than XP or others?
Sure. So the question was, why did I settle on PSL, which is a sort of esoteric solving language than some of the more common ones? A lot of things. Primarily, though, ASP is a great design tool. When you are a designer and you know exactly what you want, right? You understand this domain because you work in it and you're just looking for help. Or you want to spend a long time giving a computer a model that makes them a designer, right? For food, I am more interested in casual users, so I don't ever want a user to have to specify exactly what they want. I want there to be a lot of flex and a lot of play in how the eventual sort of solving works. Furthermore, if I'm thinking about what's for dinner, I'm thinking about a user who doesn't want to spend time. They're not working on a design tool. I'm not targeting professional chefs. To me, they already do way better than I could ever design a system for. And so when I think about what casual users and how they sort of think about systems, they're far more able to say, I think I want this, but I'm not positive. And I'm feeling it, but not a lot. And PSL lets you encode those sorts of statements in this idea of likelihood.
Nothing from chat, so.
Solid. Great. I want to stop talking anyway.
Say something briefly and close it out.
Sure.
All right. So thank you very much for watching. That was our final presentation for the day. If you did not catch all of the talks, they will be archived here on the Playable UCSC channel. And if you look at the schedule on the second page of the schedule document, which is linked to in the show notes, you'll find a number of links off to papers and various technologies that were talked about here during the talks. And there are also Twitter handles for most of the presenters who presented today. So again, thank you very much for tuning in to Generative Methods Day. I hope you enjoyed the talks. We certainly enjoyed telling you a little bit about the work here in generative methods that's taking place at UC Santa Cruz. All right, with that, I will officially conclude Generative Methods Day. Ta-da! Thank you again.
Wait till next week. Am I telling you to stop?